Hello, everyone. Good morning, afternoon, evening from wherever you're joining in. My name is Syed Mohammad Ali, and I'm really excited to be here at PyOhio 2023 with the topic of not so precise float arithmetics in Python. This is going to be a small talk, so let's jump straight into what is going to be. But before that, who am I? I'm primarily a software engineer contractor working at Arbisoft, Lahore, Pakistan. So Ubisoft is primarily a service provider company and it has like a diverse set of talents. I primarily have been working with Python and Django for quite a while. If you want to get in touch with me over LinkedIn, read something that I've written at Medium, or see some of the work that I have or GitHub, the links are here. I'll be sharing the slide link at the end of the presentation as well. And with that out of the way, let's jump straight into our topic. So let's start with what is this talk about. So here are like four one-liners of Python that we can execute on any shell. So they're just two are simple arithmetics and two are simple assertions. And let's guess the outcome. What will be if we were to run each of these line individually on shell? We would expect that the first two are simply assertion. We are adding like so not assertion like equality checking. It's like point 0.1 plus point 0.2 plus point 0.1 equal to point 0.4. The second is that's point 0.1 plus point 0.1 plus point 0.1 equal to point 0.3. The last two are simple. We're subtracting some values, and these should be the result that we would expect. They're simple maths. But if we were to run this on shell, we'll see a bit of different result. If we were to run these, only the first and the last one will give us the expected result. So point 0.1 plus point 0.2 plus point 0.1 will point 0.4. That's true. But this one is false. Point 0.1 plus point 0.1 plus 1.3, it's false, strangely enough. And for this subtraction, we were expecting 100.0, here's 100.0. But for this one, we were expecting 100.5, but it's 100.49, and it's like long repeating uh, value after decimal. So what's happening here? So this is what like relates to the topic of not so precise arithmetics float. And this is mainly happening because of float point representation in hardware. But before I jump into that, float or like these rational numbers, they are always some of them have some sort of approximation because when we represent the fractions in floats, some of them will have finite digits after decimal, but some will have infinite repeating decimals. So we the concept of finite repeating decimals and infinite repeating decimals, this tends to lead to approximation issues when it comes to infinite repeating decimals. So let's say the fraction 1 by 2 can be easily represented as zero point 0.5, but the fractions such as 1 by 3, it can be represented as 0.333 or 0.33 or 0.33. So it's infinitely repeating 3 after the decimal point. And the more threes we have, the more closer it will be to 1 by 3. But it won't be the actual value, it will always be close approximation. And same holds true for the like these other two expressions. So it's just to give the example of that. When we are talking about fractions, there will be a approximation error in general. And since this issue is in base 10, it will also be present in base 2 as well. So like other numbers, floors are also represented as base 2 or binary on hardware. So the pattern of finite and infinite repeating decimals that we saw with base 10, that also exists with binary as well. The process of converting floats into binary, that's like quite totally different process. I'm not mentioning that here, but I will mention that at the end of the week. You can see that. But coming back, so the same repeating pattern that we saw with base 10, that is present for base 2 as well. So we're representing 0.25 in binary is 0.01, but simple value of 0.1 there is some sort of pattern that is repeating, and further there might be a pattern that is repeating for a while, and then a new pattern, and then what so not. So the idea again, that approximation that we were talking about in base 10, the inherent approximation error or problem with the fractions of floats, that's present in base 2 as well. And why it tends to happen on Python, and again coming back to the point of hardware, uh, in hardware, the floats are represented in typically in 32-bit fashion, following IEEE 754 standard. And because this is hardware, like limitation issue, that the approximation error that we have seen with Python, it tends to happen with every programming language as well. So uh, in 32-bit, the first bit is reserved for sign, the next 8 are for exponent, and the remaining 23 are the like after decimal or fractional part called mantissa. So whenever the that part increases 23 bits, rounding off happens, and this rounding off leads to some unexpected approximation errors with float when we are working with any sort of application. So since this is inherently a hardware issue, how do we like work around with that? So first and foremost, if we were to go back to the initial examples, uh, our expectation were like if we were to add three like numbers and we were comparing it to the result, we expected it to work, but because of the limitations, we got a surprise. So what we can do is we can use Python's built-in route function to manually round off the values and set our expectations, expect like how we want the results to be. So instead of relying on the let's say round off that is done by Python behind the scenes, we can do the round off by ourselves in our code. So we are aware of the results that we are expecting. So built-in round function takes two arguments, number and the precision, and using that, we can get the results that we wanted. So the examples that we have at the start, if we round those two precision places, we get the as expected result in the first case, and if we round off to like 1, we get the same result here as well. If we want to work with the fractions, there is also a built-in fraction module, so we can represent those rational numbers as fractions, perform arithmetics on those fractions, and then we can format those fractions to floats wherever we need that. So this is a built-in module. We can represent like all of the rational numbers as a fraction, and we can easily perform all the arithmetics like plus, minus, multiplication, division, and whatnot, and we can easily do comparison there as well. And once we have the expected expression, or if like what sort of application we have, we can format it in the string or the float as we want to. If you want to see how close some values are, there's also a built-in math.isClose function. So we can provide the two values and calculate their closeness and set our expectation accordingly. And there we have two levels of tolerance that we can have when doing that comparison. So maximum and minimum difference that we can add in there. And using different level of tolerance, we can get different level of result. Uh, as for unit testing, the built-in unit tests also provide two assertions: assert almost equal and assert not almost equal, and they also work in a similar capacity as math.isClose. So the signature is take two numbers, the decimal places till we want to check the almost equalness, the message we want to display, and the like threshold or delta. So again, the idea is that it will take the difference of those two numbers, round off to the decimal places that we provided, and compare that value to 0 and raise assertion based upon the assertion that we have in code. Like if we're checking if the values are almost equal, and if they're not, raise that, and vice versa. And if we don't want to check against 0, but against some other value, we can also provide delta there as well. So using these workarounds and techniques, we can set our expectations in the code. The main goal when we are working with float is to avoid any surprises, because surprises can catch you off guard, and that tends to spend a lot of time in debugging and frustration. So approximation is weird, and because of hardware limitation, that will remain there. Uh, like we can use uh, long floats, 64 bits, but still the approximation issues will remain there, and that can cause our application to behave unexpectedly. So idea is that we should use the workarounds to align or set our expectation explicitly in the code so that there are no surprises. The slides are on my GitHub. I've also added my Medium article that like inspired this talk, and in that article, I've like covered over the issue that describe, and also the float to binary conversion process there as well. And there are some other links in the slides as well. If you want to read more about that. Thank you everyone for listening. If you have any feedback, questions, you can get in touch over LinkedIn. I'm really looking forward to the feedback. Thank you for being a really great audience. Have a nice day.